Yo guys, welcome back to another video. So here we're going to be focused on Fourier series for odd functions. So just to know, there are actually two types of functions. There are even functions and odd functions in particular. And these are usually the most popular types of Fourier series. Sometimes the function doesn't need to be even or odd for you to actually compute the entire Fourier series. But in this particular one, I'm going to speak strictly on odd functions. So what do we know? So we know that a function is said to be odd if the function at minus t is equal to its negative function at t. In other words, if it's symmetrical about the origin. Okay, so this is a key idea. And for an odd function, ft is defined over the range between minus L to L. So this is usually taken as a value of pi. Okay, usually when it comes to circles, or in this case, the length in radians. So i.e. a period of 2L. We find that an equals 0 for all n. So the general equation for Fourier series has an a0 and an term. And in this case, we usually only keep the bn terms. So an odd function has only sine terms in its Fourier expansion. So this is really all you need to take from here. So an odd function has sine terms only, whereas an even function has, you can guess it has actually all terms. So the general Fourier series for an odd function is given by, and now take note, so it's ft equals the summation from n equals 1 to infinity of bn, a term, times sine n pi t over the period, over half the period L. And bn is also equal to this integral. So it's 1 over L, 1 over the half period times the integral of the total period 2L, or L to minus L, times the function that you're observing, times sine n pi t of L. In this case, we're just going to express an equation. We're not going to actually compute the summation completely. We just need to find the integral, pop it back in, and voila. So let's check out an example that's been presented by the University of Portsmouth. So in this example is from a course and one of the particular tutorial sheets. So for an odd function, ft is defined according to this one. So we can see that ft equals minus 2 between the range minus pi to t and at point 2 from 0t to pi. It's from 0 to pi. And for every 2 pi radians, it's equivalent. So this is purely symmetrical. So just to have a final key idea, how does the graph actually look like? Just to have a general understanding. Well, take it like this, yeah? So let me just, here we go. So let's just draw a straight line here. So this just be a rough sketch. So from t, let's call this axis ft, so the function of time, and the x-axis here, let's call it t. So between minus pi to t, so we can say this range here, so let's go up in pi, so this be pi, 2 pi, and so on. Minus pi, minus 2 pi, minus 3 pi, and so on. So between minus pi and 0, this would be a value of negative 2. We can call this line negative 2. And between 0 to pi is positive 2. So let's put this as 2 and minus 2. And you can see for every 2 pi added on, we move to the next line. So it'll be here. And the same thing, the next one would be here. And of course, going 2 pi back, this must be here. And then this must be here. So you can kind of see that it's in the verge of pi's. So this is purely symmetrical. So in a way, so this is still a continuous function. There is no actual gaps. It just quickly jumps from 2 to the next one. And there is, yeah, as you see, there is no gaps. So this is clearly symmetrical. So this is what you call an odd function. Symmetrical about the origin. Okay, so let's actually solve the question. So here we're trying to find the Fourier series of this function. So without further ado, let's jump in. So solution. The key idea firstly is to recall the equations, right? And all we need to do is pop in the value of bn. So what is our value for L? Well, L is actually the range. So because we're going from minus pi to pi, we can clearly say that L must be in the verge of pi. So this L works as the interval. Okay, and the function t, well, is split into two parts, minus 2 and 2. And because the range is from now minus pi to positive pi, we need to split this as two integrals, going from minus pi to 0, evaluating the value minus 2 sine, and from 0 to pi, evaluating positive 2 to this interval. So let's write this down here. So therefore, we can clearly say that, let's have a look, bn must be equal to pi times the integral of, let's have a look, between L to minus L. So the first interval will be minus pi to 0, so let's put it over here. So minus pi all the way up to 0. So I guess I should do a bracket as well. So always do a big bracket outside. And then this would be minus 2 sine n pi. And if you look at the formula, it will be n pi t of L. Since L is pi, the pi's cancel out. So it'll just be sine nt. Okay, dt. Plus, and then we do another integral covering the other ranges. Is from, let's see, 0 to pi. So 0 to pi at the point 2. And this would be sine nt. Easy stuff. Okay, not bad. So that's what we do. Now we just evaluate these integrals. And that's quite easy. So I'm going to quickly just change the color of my pen. So key step is find these values and now integrate them. So first things first, because we're integrating sine, it's going to quickly become a negative cos. And we just pop in limits. So this would be minus 2 cos nt. And because the sign flips, will become a positive. So it'll be positive 2 cos nt over, and we just the differentiate inside, so nt becomes just n. And we'll repeat the same here. This will now be on the right side a negative 2 cos nt. Okay, so at this stage, one thing you want to just quickly simplify and notice that everything is over 2n. So we got 2n on this side, 2n on this side. So we could just push it to the front line. And once we have that, we should have something like this. So 2 over n pi, and then inside we just left cos nt and cos nt with the limits 0 to negative pi and pi to 0. Now let's go ahead and evaluate each term. So first things first, so when you plug in 0 in place of t for cos t gives us exactly 1. Yep, just double checking that. So where's my pen gone? So cos 0 equals 1. If you plug in a negative pi, you're going to have cos minus n pi. And actually, just to do a quick test, if you plug in any value for n, you'll notice that this is symmetrical. So this is also the same as cos n pi. So that's convenient. Now for the right side, what you're going to have, so plug in pi, you're going to have the same thing, cos n pi. So that's 2 lots of these. And if you plug in 0, again, you get 1. So cos 0 equals 1. So what does this mean? So this means that the value of bn must now equal, so we're going to have 2 over n pi all inside the bracket. So we're going to have 1 minus cos n pi minus cos n pi. Instead of minus, it will be plus 1. So our final solution is going to be 2 minus 2 cos n pi. So if you're going to refactorize this, you can pull out a 2. So you're going to be left with 4 lots of over n pi. And then you'll be left with 1 minus cos n pi. Okay, not bad. So what does this tell us? So we have to make a few deductions here. So the thing is this one, we need to see what happens with a certain value of n. So let's take, I don't know, let's say when n is 0. So let's make a couple of deductions. I'm going to do a new page, copy this down. So we're going to have so far bn equals 4 over n pi times 1 minus cos, let's say n pi. So when n is, so n can't be 0 firstly. So let's say when n is 1, what do we have? So we have cos pi. Just to double check, cos pi will give you negative 1. Cos 3 pi will give you negative 1. So for any odd numbers of n, so we can say when n is odd, which is even better. So the whole point of this is to test what happens when n is odd or even, barring except 0. So when n is odd, we're going to be left with a negative 1. So we're going to be left with bn equals 4 over n pi times 1 minus 1. So 1. So this becomes a positive 2. So it'll be 4 over n pi times 2. So it'll give us 8 over n pi. Now, and this is for, just to make it clear, when n equals 1, 3, 5, and so on. So test this in your calculator. You'll see that this entire value of cos n pi becomes -1. So when n is even, what do we get? So just test out. So let's say cos 2 pi, for example. You get a +1, or cos 4 pi, you get another +1. So you're going to get 1 minus 1, so you're going to get a total value of 0. So in this case, we need to make sure that n is odd, otherwise we cannot get an actual finite solution. So we can say finally, to wrap this up, so when n is odd, our function t can be written as a Fourier series in the form of the summation from n equals 1 to infinity, and then looking at it carefully, so bn gets replaced with 8 over n pi, and yeah, we got 8 over n pi, and just look at this one here. Since L is pi, these two cancel out, so we're going to be left with, try and do this in one go, 8 over n pi times sine n t, and that's it. That's really it. Or obviously when n is even, then the function is going to be 0, because since bn is 0, 0 times this will give you, well, 0.